Section: Introduction. In this section, we discuss the importance of reasoning skills for large language models, LLMs, to reach human-like intelligence. We note that recent work has aimed to improve these reasoning abilities after the initial training phase. Most existing methods depend on supervision, which can be categorized into two main types. The first type is supervised fine-tuning, where we need well-annotated responses paired with specific queries. The second type involves reinforcement-like methods that require either correct answers or some form of verification. While the first type works well in areas like math and coding, many other problems do not have clear solutions, making it hard to generalize to broader reasoning tasks. The second type uses an external reward model for verification, but creating a generalized reward model can be costly and may lead to issues like reward hacking. Given these challenges, we are motivated to explore how we can enhance LLM reasoning without any external supervision. To address this, we introduce a self-training framework called Genius. Genius operates solely with the LLM and a set of unsupervised queries. It follows a self-training approach where the LLM generates responses based on input queries and selects the best ones for training. This initial attempt aims to help LLMs improve their reasoning using general queries without external help. A key challenge in generating training data for self-training is figuring out how to evaluate LLM responses without outside resources. One straightforward method is to have the LLM create a full response and then assess it based on its confidence in the sequence. However, most current methods focus on rewards at the response level, while stepwise supervision could lead to more stable training. Some recent approaches use step-level sampling but still face limitations due to their short-sighted nature. Search-based rewarding methods offer a broader perspective but are often slow and complex. To overcome these issues, Genius seeks the best response sequence through stepwise sampling and gathers high-quality preference pairs with rewards. Instead of relying on external supervision for a global perspective, Genius uses a simple method called foresight, which estimates future steps and evaluates them based on uncertainty. We propose a stepwise foresight resampling approach that uses foresight scores to guide the next steps and create preference pairs. While this method balances quality and efficiency, calculating foresight scores from a few rollouts can lead to biased estimates, introducing noise into self-supervision labels. Previous self-training methods have typically used either supervised fine-tuning or reinforcement learning without considering the uncertainty in self-supervision. We address this by introducing an advantage-calibrated loss function, which penalizes inconsistencies between foresight scores and step advantages. We find that this approach improves training stability and performance compared to traditional methods. Genius presents a novel perspective on post-training, showing that LLMs can enhance their reasoning abilities using general queries without external supervision. With just 25,000 unsupervised queries, Genius significantly boosts average performance across various reasoning benchmarks. We also observe that the scaling law for general queries improves consistently with more training steps. Given the vast amount of general data available, this scaling can greatly enhance reasoning capabilities and push the limits of reasoning scaling laws. In our methodology, we highlight that Genius only requires unsupervised natural language queries as inputs. In the self-training setup, the LLM generates responses based on queries and selects the best ones for optimization. Genius has two main objectives: 1. To synthesize and reward responses, and 2. To optimize the LLM using these responses. We model responses as sequences of steps, deriving the best response through stepwise sampling and rewarding. At each step, Genius rolls out candidate steps and self-rewards them by simulating future steps. We then select the optimal next step and gather preference pairs for training. For optimization, Genius calculates step advantages during sampling and uses them to enhance the LLM with a specially designed reinforced loss. We define symbols for clarity, where the current step is denoted as A, with its value, and we represent previous and future steps accordingly. Section Summary. In this section, we introduce Genius, a self-training framework that enhances the reasoning abilities of large language models, LLMs, using only unsupervised queries, eliminating the need for external supervision. By employing a stepwise foresight resampling approach and an advantage-calibrated loss function, Genius effectively synthesizes and rewards responses, leading to significant improvements in reasoning performance across various benchmarks. Section: Exploration and Exploitation via Foresight Resampling. In this section, we explore the concepts of exploration and exploitation through a method called foresight resampling. To maintain diversity, we employ a beam search strategy during our sampling process, defining the step beam size as m. For instance, when m equals 2, we illustrate this in our figures. At the previous step, k1, we keep m paths, each containing k1 steps. We assign a value to the last step in each path, referred to as q for that step. For each beam, we generate n candidate steps, resulting in a total of m times n candidate steps. To overcome the limitations of auto-regressive generation and to create a globally aware response, we simulate future steps based on each candidate step. This simulation process, which we call foresight, allows us to derive a response sequence along with foresight scores, calculated from the average log probability of the remaining steps. With these simulated future steps, we can construct a complete response. We obtain m times n foresight scores, which help us approximate a distribution. After normalizing this distribution, we can identify the foresight score at each index. We also use a temperature parameter to adjust the distribution's sharpness. Using the foresight technique, we select steps for the current timestamp by sampling from the foresight score distribution. This enables us to maintain m beams for exploration in the next step. We define the Q value of each selected step using its foresight score. Additionally, we exploit the entire response sequence at each timestamp for optimization. To promote diversity and prevent overfitting, we implement a resampling strategy based on the foresight distribution. The response with the highest foresight score is chosen as the positive response, while a negative response is resampled from the same distribution. This strategy helps us balance exploration and exploitation. Since the reasoning sequences come from different beams, we cannot simply evaluate each step using the foresight score. Therefore, we derive an advantage value for both positive and negative response sequences, calibrating the foresight score with the Q value from the previous step. This allows us to construct training preference pairs in a specific format. For our training data, we source queries from two general corpora, MagPi and another source. To manage computational costs, we randomly select 25,000 queries from MagPi and 32,000 from the other source for self-training. To evaluate the basic reasoning abilities of our models, we include several benchmarks for different types of reasoning, such as GSM-8K in math for math reasoning, Reclor and Logica for logical reasoning, and others for general reasoning. We also incorporate general benchmarks to assess performance stability and a competition-level benchmark to demonstrate scalability. Our baselines consist of two categories, one requiring supervision beyond the training queries and another that only needs unsupervised queries. Further details can be found in the appendix. Section Summary. In this section, we describe our approach to exploration and exploitation using a foresight resampling strategy, where we utilize beam search to maintain diverse candidate paths and simulate future steps to derive foresight scores for optimizing response sequences. We also outline our training data sources and evaluation benchmarks to assess the reasoning capabilities of our model, ensuring a balance between exploration and exploitation through a structured resampling process. Section: Base LLMs. In this section, we utilize Llama 3.1-8b Instruct as our main model for the experiments. To test its ability to generalize, we also apply self-training methods to the Qwen 2.5 Instruct models, including the 3b and 7b versions. For our training and inference setup, we configure the foresight sampling with specific values, 2 for m, 4 for n, and 4 for k. This results in a total of 100,000 training pairs for Magpie and 128,000 for OpenHermes 2.5. We speed up the inference process using the VLLM engine, with more details available in the appendix. In our main results, we present evaluation outcomes in a table, showing both individual dataset results and average performances in the last column. We find that Genius significantly enhances the reasoning abilities of Llama 3.1, outperforming all strong baselines. With just 25,000 unsupervised training queries from Magpie, Genius improves the average chain of thought reasoning performance of Llama 3.1-8b Instruct by 7.43%. This improvement is even more pronounced when using OpenHermes as the training data. Genius consistently shows state-of-the-art performance, with an average advantage of over 2% compared to strong baselines, especially excelling in challenging tasks like math, where it outperforms self-rewarding by more than 4%. Genius maintains its superiority across all evaluation benchmarks, while other baselines, such as CO and SPIN, show varying performance. We observe that self-training with reinforcement learning (RL) optimization is more effective for enhancing reasoning with general data. Among the baselines, RL-based self-training methods, like cobalt-1 hydride, self-rewarding, and SCPO, consistently outperform supervised fine-tuning methods, such as SFT and STAR. Since current large language models, like Llama 3.1, are already optimized for chain-of-thought reasoning, we find that RL is necessary to develop broader generalization capabilities, rather than relying solely on supervised fine-tuning to instill reasoning patterns. Interestingly, we note that supervision from ground truth responses does not lead to improvements, while self-generated responses effectively boost performance. Regarding performance consistency on general tasks, we find it challenging to maintain performance on general benchmarks after post-training. Using the Open Compass evaluation suite, we test 6 widely used general benchmarks, categorized into subjective and objective evaluations. Our results show that Genius maintains stable performance in the general domain, with slight improvements in most cases. Notably, self-training with Genius leads to significant performance gains in the Arena Hard benchmark, indicating better alignment with human preferences. For knowledge-intensive benchmarks like Wikibench, MMLU, and MMLU Pro, Genius preserves the performance of the base LLMs, avoiding catastrophic forgetting after post-training. We also analyze Genius's generalization and adaptation capabilities to different backbone LLMs and competition-level tasks. In addition to our experiments with Llama 3.1, we evaluate the Qwen 2.5 series. Our findings show that Genius achieves the highest performance gains over the base LLM across 7 benchmarks for both Qwen 2.5-3b Instruct and Qwen 2.5-7b Instruct. However, self-training on Qwen 2.5 models does not yield greater benefits than on Llama 3.1-8b Instruct, and some baselines even struggle in certain cases. One possible explanation is that Qwen 2.5 Instruct has undergone extensive post-training, making further improvements difficult. This does not contradict our main contribution, as Genius serves as a versatile post-training technique, functioning as both an ongoing self-training method for post-trained LLMs and an alternative post-training strategy. Lastly, while Genius is not specifically designed for training large reasoning models like DeepSeek R1, we find it valuable to evaluate its performance on challenging problems. Our experiments on the competition-level task AMI 2024 show that Genius boosts performance by 6.67% when trained on OpenHermes 2.5, split from Llama 3.1-8b Instruct and Qwen 2.5-7b Instruct. This confirms that Genius not only enhances the fundamental reasoning capabilities of LLMs but also expands their potential to tackle more complex scenarios. Section Summary. In this section, we demonstrate that our method, Genius, significantly enhances the reasoning abilities of the Llama 3.1-8b Instruct model, achieving a 7.43% improvement in average COT reasoning performance with only 25K unsupervised training queries, while also maintaining stability across general benchmarks and adapting effectively to different backbone LLMs like Qwen 2.5. Our findings indicate that self-training with reinforcement learning is more effective than traditional supervised fine-tuning, particularly in challenging tasks. Section: Ablation Studies. In this section, we explore the effectiveness of the key contributions of Genius by conducting ablation studies on the sample and reward strategy and optimization objectives. For the ablation of the sampling strategy, we present our results in a table. First, when we remove the foresight module, we observe an average performance drop of about 3.17% to 3.25%. This indicates that the foresight sampling strategy helps reduce the short-sightedness in language model generation, and using the foresight score enhances the self-rewarding aspect of the step value. Additionally, when we switch to a greedy selection method for sampling, we see significant performance declines. This confirms that our resampling strategy effectively balances exploration and exploitation. Next, we examine various optimization methods, including DPO, SIMPO, IPO, ROPO, and SFT, as shown in our table. Among these, our ACO loss function demonstrates notable advantages, leading to an average performance improvement across 7 reasoning benchmarks. Compared to the robustness optimization strategy ROPO, ACO proves to be more effective in self-training scenarios. Regarding post-training scaling, we acknowledge that our computational resources limit us to 10,000 training attempts, which we present in the main table. To guide future post-training scaling, we provide down-sampled scaling curves in a figure. Our findings suggest that Genius has significant potential for scalability. The figure shows that Genius can quickly self-improve with limited training steps, and the progress remains steady as training steps increase. This indicates that self-training with Genius is not yet saturated and still has room for enhancement, while other baseline methods struggle with scaling. In the context of post-training for LLM reasoning, we note that enhancing LLM reasoning through post-training has gained attention recently. Some approaches utilize large-scale imitation learning on well-curated reasoning data to develop large reasoning models for specific domains, like math or code. Due to high annotation costs, recent efforts have shifted towards self-training techniques to generate reasoning trajectories more efficiently. However, these methods still depend on supervision signals and in-domain training data, either through explicit outcome supervision or auxiliary reward models. In contrast, we take a different approach by focusing on self-improving the general reasoning ability of LLMs without any supervision. Lastly, we discuss optimization techniques. Previous research often relies on supervised fine-tuning to introduce new reasoning patterns into foundational LLMs. With advancements in stronger models, some efforts have turned to reinforcement learning (RL) solutions to enhance LLM reasoning, demonstrating the scaling effect of RL with outcome rewards. In our work, we propose a novel RL objective for robust optimization in an unsupervised setting, revealing a promising scaling law for self-training with RL optimization.